Today's topic is data acquisition with the PSoC circuits. I think I will first use the whiteboard just to explain what kind of thing we are going to build today. And okay, there we go. Setting up the video at the same time. All right, so data acquisition system, typical parts. Have you already taken some electronic measurement system technique or something like that? That kind of course, maybe. Some of you, yes. All right, but anyways, if we have any sensor, well, there are some sensors there. The easiest sensor actually is just a potentiometer, because I noticed we also have some temperature sensors, LM35s. That's the most burnt device in the world. You just accidentally switch the polarity and it will burn. Smoke comes out of it and it doesn't work anymore. So, okay. So, but anyways, there are also variable resistors there. Nice sliding ones right here for testing, and then for the real stuff you need to use the, well, burn some sensors. Okay, that's our, the testing device. And what is the data acquisition system? What are the main parts? You might actually start with some amplifier, right? Usually the signal from sensor is very small, so you need to amplify the signal before doing the A to D conversion. Then you might actually have an analog low-pass filter. If you have noisy source, small signal usually have some noise. So the low-pass filter, and then you would have the sample and hold circuit, and then you have the A to D converter. All right, there we go. Then you have data. So that is a typical system. Okay. Sample and hold is synchronized with the A to D conversion, and there you have the sampling clock. Okay. So sampling clock is actually defining the times when you take the sample. You can also run a, for example, if I'm measuring temperature and don't want to have any time information, you just, take those samples whenever you need. But actually, to do any sensible signal processing afterwards for the data, then it's better to have uniformly sampled data. Right. Have you taken the digital signal processing course? Digitale Signalverarbeitung. Okay, remember that one. It's the uniformly sampled data. Then you can do digital filtering. In this exercise, actually, you'll be doing some digital filtering. So basically, a simple the sample rate conversion. Sample rate conversion meaning actually that block is not just sample rate conversion, but it also needs to have the low pass filter, and then you have the downsampling. And whatever comes out comes out. And here we have a different sample clock. So here we have the primary sample rate, FS1, and then we have this secondary sampling rate. Actually, this is downsampling the data. Downsampling because it basically then reduces more noise. It's better actually to oversample the data and then do some averaging, and then you may actually have better results. well, less noisy at least. It doesn't make this sensor any better than it is. If it's 0.5 degrees is the accuracy of the sensor, averaging does not change that. It's still the same in accuracy. Okay, but anyways, so that kind of system you will be doing today. And of course, we have this nice LCD where you put the result. Okay, good. What is inside of PSoC? All of that. No, not LCD. But it has the interface for LCD. Okay, all of this you can find from the PSoC. So they have the amplifiers, analog amplifiers, even analog filter, sample hold, and A to D basically. This is just one block. They call it analog to digital conversion. This, of course, comes from some interrupt routine or whatever. And as a matter of fact, actually, now we have a free running, continuously running A to D converter. So roughly at sample rate, this one is about 100 samples per second, in that range. While this display, well, display is kind of slow device. So basically, the display, this second sampling rate is about 2 samples per second. Okay. So in principle, what your program should do there is to have a free running okay, we skip that one, but not really. Actually, this is okay. Let me think it over. Yeah, actually, it works. It works. Yeah. So basically, this is free running. We have roughly 100 samples per second, but here you should have about 2 samples per second. This you can do. This timing you can do with the sleep timer. Which basically wakes up twice a second. You have done actually that kind of thing already. That blinky was waking up twice a second. Okay, now you are not blinking the LED. Well, you can still blink the LED, but most importantly, you will calculate the on this main loop. You will be calculating this the average temperature, which will be actually the sum of the temperatures divided by how many measurements you are taking. Meaning this one here, at some point, you should actually calculate these running sums. The correct place to calculate would be, guess where? The A to D converter interrupt service routine. That's where you calculate the stemp plus equals to current A to D value, and then the ntemp, increment that one. Right. Something like this. So, okay, so any sensor, in your case, it's the temperature sensor, but before trying with the temperature sensor, you should actually try it first with this just potentiometer. I think this board also have some sort of, yes, it has the potentiometer there, but if you want to use a separate one, that's just fine, since you still need to make the wiring for your sensor. So why not to just do the wiring for that, so that you can actually later on just switch the LM35 there. Okay. So testing with variable resistor, then measuring with the temperature sensor. Okay. Yeah. So amplifier, analog low pass filter, sample hold A to D. For for the exercise, I will put the analog low pass filter as in parentheses, since that's kind of extra stuff. You can do it if you want to explore that point. This sensor is low, so you don't necessarily need this analog low pass filter. Okay, so yeah, that's what it's all about. So data acquisition system, the gain, low pass filter, A to D conversion, then downsampling on software, and showing the data on LCD. Good. So how to do those things on the device? This my designer there. Good. Let me start with from the scratch. Just rename it and click OK. And the parts what I need there are gain, okay, amplifier, programmable gain amplifier, PGA. Just click that one, and it appears. On digital blocks, it usually does not make any difference where you put the digital these devices, but actually on analog blocks, it makes difference. For example, this here can take signal only from odd pins of the port 0. So this is analog multiplexer, and it actually shows that, okay, I can take the signal from port 01, 03, 05, and 07, but not the even ones. All right, so if you want to have the signal input from the for port 00, then this gain block must be actually on somewhere else. For example, on that one. That actually can have the signal from port 00. Okay, or well, whatever port. It also can actually be switched to the this another multiplexer. So practically, if you want to have all 8 analog channels and have a analog multiplexer for all 8 channels, then you basically have to have the gain block here, and then you have these 3 different multiplexers here to play with to route the signal to your the programmable gain amplifier. Oops, PGA. Okay, some parameters. Actually, so of course, what is the gain? We can actually start with the gain of 1 for this exercise, because actually if you have a potentiometer, then you get 0 to 5 volts, and our A to D converter is usually 0 to 5 volts. Or is it? Oh, we'll take a look at that one. But this actually is the gain compared to the current reference level. And what is the current reference level? That depends on a lot of things. Okay, but input is from the analog column input select 1. So from this multiplexer, 2-to-1 multiplexer, you have the input there. Reference. Okay, now we are talking something weird. So reference level can be selected from different sources. You can select it from block ACB00, which gives basically you a lot of freedom on having a programmable reference level for the amplifier. Analog ground. Analog ground depends on the global settings. And the global settings actually are right here. And it basically gives you the reference multiplexer. So that's the internal reference for signals. To have any accurate results from A to D conversion without the operating system voltage level, then you need to reference everything on the band caps. If you are sure that your processor runs on flat voltage, which is regulated within, say, less than 1% or so, then you can run all the analog systems also from this reference. But my favorite here is that to select the reference level to 1.6 times band cap plus minus 1.6 times band cap. Band cap here is 1.3 volts. So that 1.6 is roughly 2 volts or so. You can actually find it from the data sheet. So basically, that's 1.6 times the band cap, and then basically plus minus that. That's 2 times 1.6 times the band gap, and 0 volts. So basically that's a good setting for the analog signals. This also sets the level of the A to D conversion, the range for, the range for the A to D conversion too. More information about how to select the band gap is actually in here. Selecting analog ground and reference. Okay. Let me open it. Adobe. Okay, there we go. So that's the ground and reference structure. So it's quite complex system. And yes, you can also have their external sources for the reference if needed. Okay, and here we have the band gap circuit. So basically, that's a cheap alternative for a good voltage reference. And band gap is about 1.3 volts. And yeah, depending a little bit of the temperature of the chip. There's also a small dependence there too, but it's really within, say, it's 20 plus minus 20 microvolts, 1.3 volts, plus minus 20 microvolts. Pretty good for a this kind of cheap voltage reference. All right, so band gap voltage was 1.6. So basically 1.6 plus minus 1.6 band gap means roughly 2 volts plus minus 2 volts, which means that actually it's quite easy also then to do the conversion, rough conversion of the millivolts to, or actually the A to D conversion to millivolts. So 4 volts is quite close to 4.096 volts. Okay, but anyways, so now my band gap is, the voltage reference is between 0 and 4 volts, and the middle of it is 2 volts. There. Okay. Nothing important there. Okay. Back to the business. So I have the band gap reference, 1.6 times band gap reference marked there. Good. And then I can actually, on this one basically, okay, on the first programmable gain amplifier, I could use the also the zero reference, the real the operating system, the operating volt is 0, because I already know that my sensor is referenced to 0. Okay, so that one I would actually connect to BSS. Analog ground would mean that I'm amplifying signal reference to 2 volts. Okay, so be careful when you are selecting the source for references. This is good reference for A to D conversion, yes, but for amplification, although it looks like single-ended, it's differential amplification because you are selecting the reference level. So this amplifier actually is like that. So you have a gain, you have input, and this one is basically on A reference. If you here use the analog ground, you will get funny results with any other than gain equals 1. Okay. Analog bus. All right. So this we will disable, since practically you can actually also take this output of the amplifier and put it on some pin. Okay, it could be useful sometimes. For example, if you wanted to make some just programmable gain amplifiers with the PSoC circuit. Okay, that would be one way. You just have a small program, some button input, for example, to change the gain of the block, and then input and output, and that's it. What you need to do, and then you have a programmable gain amplifier circuit. Okay, but now I just disable that one. By the way, these analog output buffers, this can be connected only to port 05. This would be port 03. I think that's the port 4, pin 4. That's port 0, pin 2. So only those 4 pins are available for output. Okay, and that, of course, then says in which block you would need to put that device. Okay, now we have gain. Let's take a look at the analog filter. And with some luck, we even may have space for a 2D converter. Okay, filters. Filters, these are all switch capacitor type filters, and that's the low pass filter, second order low pass filter. No need to do the fourth order, I think, since that would take more of the blocks, and gain is not that great. So low pass filter 2. Let's see what happens. Okay, so basically what you need to do is now to select the topology. If it's the first here is topology that actually shows you it takes 2 blocks, 2 switch capacitor blocks. Okay, and let's see where I can put this one. So we have the programmable gain amplifier on ACB01, and the output of that can go to, on this topology, it can go to here. I think that's just fine, maybe. Is there anything else? Okay, well, this topology also have the input from here to there. Okay, but anyways, this is something you may need to play with to get everything fitted into the these blocks. I'll just use the first one and see if it fits. If it doesn't, then try something else. Okay. First thing to do here is to check that if we can route the signal from this programmable gain amplifier to this filter. ACB01, excellent. So I can take the signal from the that programmable gain amplifier to my filter. So the next step would be to take the low pass filter to wizard. You can always start guessing the capacitor values and clock rates and that kind of things, but I think it will take a little bit time to get anything done. Are you familiar with the switch capacitor technology? No? Yeah, I know. It's old school. I'm a dinosaur. I'm the dinosaur here. Switch capacitor technology was cool technology when I was young. Okay, let's take it this way. we have one switch here, another switch here. They assign two different voltages, U1 and U2, and we have capacitor right here. Okay, so when we switch this on and that one is off, then we actually charge the capacitor to voltage U1. Okay, when we switch basically that off and that on, then you discharge the capacitor there, and that charge actually is, let's see, how does it go? I equals dq per dt times c, right? But anyways, so you basically transfer a charge at rate of some clock frequency, meaning that actually you're not doing dq or dt times capacitance equals current directly proportional to the switch in frequency, which means, okay, this is actually a resistor. It acts like a resistor if the frequency is high enough. Okay, so it's quite smart way of making variable resistor that you can control digitally. Simple device that it can be easily integrated, since the resistors are hard to integrate on any integrated circuit. Capacitor is easy. Switches are easy, those are just MOSFETs. And that way you actually have a variable resistor. Yeah. So that one actually looks like a variable resistor where you vary this one with the clock rate. And when you have a variable resistor, then you can, of course, start doing the Allen key structures on integrated circuits, and which means that you have a variable properties for that filter. So basically, LPF2 wizard helps you defining those the basic capacitances here, and also the cutoff frequency. Okay, good. So some parameters we need to do here. First of all, yeah, there are different types, but there's not too much of difference on those different type filters, because this switch capacitor filter technology actually does this one to you in any case. So basically you will get on higher frequencies you will get some effects due to this technology. It doesn't go as as the analog filter would do, but it's much better than nothing. Much better than just RC filter. Okay, so let's see, corner frequency. Currently the corner frequency is quite high, so it's set up for the highest possible clock frequency, which is 48 megahertz clock frequency. That's the doubled system clock rate. Okay, I want to have a lot of attenuation at 100 samples per second. Right. Or actually, no. 50 hertz. Yes. So I need to scale this one down quite a lot. Let's see, how can we do it? How can we do it? Okay. Flexible like this. I just played with the numbers. So the sample rate on this one, F sample, is actually this clock rate, not the sampling clock rate. Okay, but it's still, okay, I need to do a little bit better than that. Maybe something like this. Okay, so I have a cutoff frequency at 10 hertz, which means that at 50 hertz I have 20 dBs of attenuation, and that 50 hertz would be roughly my Nyquist frequency for this system. Remember, from the digital signal processing, you need to, in order to prevent aliasing, you need to do it like that. Right? Maybe. Which clock? About 120. 100. This one. Oh, there. Yeah. 480. Yes. 480 hertz column clock. Yes. You probably don't have this done yet. So the corner frequency 10 hertz, and actually I don't remember this actually, you play a little bit with that to see what is the when you get the best one. I think it was the okay. So you may actually need to play with the sample clock there to get it the attenuation right, but it's more or less just eyeballing when it looks good. Okay, so for this filter now, basically the column clock is 400 hertz, and if you say okay, it sets the capacitor values in the system. So now we just need to find a way to produce 400 hertz signal from 24 megahertz. So we need some dividers. This 480 would be better value, right? Since then, 24 megahertz divided by 480. It doesn't make any difference. Okay, so again, let's do the same math as yesterday. So we start from 24 megahertz, and we have 400 hertz here. What is our desired? 60,000. Someone said 60,000. Yes. Is it 60? 60K. A little bit too much for those dividers VC1, VC2, VC3. So we need to do something else. Actually, there is a way also to divide 32 kilohertz clock, which would probably give you closer. But anyways, I think we'll need to have another divider. All right, how much this is dividing? Say 10, 100. You can get easily, say, 20,000 from that one, right? 10, 10, and 200. Those busy clocks. But okay, now pay attention. If you are using these clocks to something else, then you need to actually do add some digital blocks to produce that clock rate. But this is just one example. Tomorrow you will need to change this in any case. Tomorrow you will be continuing basically from this design, but making also connection to the computer using serial port. And there the serial port baud rate actually dictates the clock rates. Okay, but well, that's tomorrow. Let's not worry today. Just like, the British people a couple of years ago, let's exit the EU. Let's worry to later. Oh boy, what a mess. Okay. So, counter. 8-bit counter would do. I just need to count down that one. Okay. 3. Divide by 3. And this counter, the clock is coming from VC3. Clock sync always sync to this clock. Yes, enable. Compare out none. Terminal count should go somewhere. Somewhere where we can actually connect it here. Okay, how to do that one? So it's basically we have these analog clock systems. For example, for this column, analog column clock. Okay, so it's nice to have this kind of nice switch matrix with lines, but one small thing is that you need to find a way to route the clock up from that block to this device. And I can do it from here. Okay, VC1 or VC2 or analog clock 0 select or analog clock 1 select. Let me take a look if I say analog clock 0 select, and that goes here. Oh, right, so here I can actually take the signal from DBB00. There we go. Now that clock, the divider actually is now connected to as the signal. Another modification. This now has a kind of bad divider, number 3. You don't really get a symmetrical clock rate using that. It would be better to have this one, for example, 6, and that one 10K. Then you can actually have the symmetrical clock coming out of that one. Which means that that divider is 100. And here we have no compare out, terminal count, none, period, 6, compare value 3, less than, interrupt type, well, it does not make any difference here. There. Okay, those settings. So clock is VC3, which is now I have the VC3 set up at 10 kilohertz. It's 10, 10, 100. That gives you 10 kilohertz input clock. Sync the system clock. Enable, yes. Compare out and terminal count. We don't need those signals out to any pin, since we are using this internal signal there. Okay, period 6, compare value 3. Compare type is less than, interrupt type terminal count. Well, it doesn't actually make any difference. We are not using the interrupts. Yes? Symmetrical clock. So 3 counts here and 3 counts here. Just in case. Okay. I don't know if that actually makes much difference, but all right. So now we have a low-pass filter. We have program gain amplifier, low-pass filter. Next step, let's try to find a to D converter that fits the purpose. Yeah, there. Lots of A to D converters to choose from. All right. So, are you familiar with different types of A to D converters? Yeah, you have heard of them. Okay, good. So, incremental A to D converter. Well, it's also called single slope integral. So it just integrates until this the constant slope is equal to the input signal, and then it calculates how many counts it was. It's a nice one way of doing the. But I think that there are also some other A to D converters. Oh, but okay, let's see. So this one has 6 to 14-bit resolution. That's nice. And other stuff like that. Usually, actually, for some reason, these chip manufacturers, they like delta sigma, which is not the best solution ever. It has lots of resolution, but accuracy is not that great. It's because it loses the zero level at some point in any case, unless it's recalibrated once in a while. Okay. Then there are these easy A to D converter. That sounds good. Okay, easy to use. Successive approximation register. So that's same as the Newton's halving method of finding the value, which basically is usually fast and rather accurate, as long as your signal stays stable when you are doing the conversion. On the other hand, here this successive approximation register A to D is only 6 bits. Nah, that's not good. So basically, we could try the easy A to D converter and see if we can fix that. All right, and it looks like it's also the it has either first or second order modulator. So this is practically looks like delta sigma topology. Well, who cares? As long as we get bits. You can always, if you have a to D converter, you can always go and afterwards do the calibration and with the PSoC circuit, the calibration can be done by software because of the band gap. You can have the by software you can connect this band gap input right here and fix 1 point. Do a 1 point calibration anytime. You can also do 2 point calibration by let's see. Yes, of course, you can set the gain, for example, at 0.5, and then you have 2 points where you can do the calibration. Okay, but anyways, that's just fine. Signal order. See, yes, it actually goes there. Now my question is, can we take signal from here to there? So let's see. Input signal. Oh, where's the input signal? Input is from block. Oh no, it's coming from this one. No, that's not good. Can we actually change that one to ASD? No, we cannot. Okay, we have to do something. So basically, you can take it from the input select. You can take it from ACB03. You can take it from analog ground, ASC12, ASC13, but our signal is actually right here at ASD. ASD20. Okay, let's see if we can move that one there. And do we have any luck here? Input. No, still can't do it. That okay? Yeah, that requires now a little bit of fiddling of where to put anything. One way would be to route the signal out from this block to output pin and take it from multiplexer. Yeah, I know. I know, that's one way. Okay, the other way, we can always try to get the signal from, let's see, does it allow ACB02? If we can get this signal to amplifier block, then we might actually be able to reroute the signal. Let's try that one. Just adding an amplifier. Another amplifier. Not here, but there. At least I can take the input. Okay, where's the input? Input. Okay, not reference low, but ACB02. Yes, I can take that one, and then the input for that one, ASD. No, still no luck. Yeah, I know this is annoying. Cannot use that one. Move that one back to that one. Another way would be to try to move that filter here. And let's see. Still no luck. How about here? Can't move it there. Okay. That's a bummer. I think we are out of options, and we have to route it through a pin. So there, analog output bus. that one, so port 03, and now we have signal on port 03. This multiplexer is even, so we need to actually move that one back here and take the signal to this one using that. Yeah. So so did you get all messed up? I did. So my signal, original signal comes to port 00, and then it goes to the PGA. Then that output is going to low pass filter block here. The low pass filter block output goes to the buffer, which is connected to port 03, and then port 03 is actually connected to this multiplexer, through this multiplexer to my A to D converter. Done. What? Which? Column clock? Column clock is coming from wait a minute. Oh no, it messes up our clock signal for that block too. This is mess. This is a big mess. Now we don't have the clock anymore for this. Since this can take the clock only from, well, let's see, can it take it from analog clock? Okay, there. Okay, yeah. So this one actually messed it up, since because the easy A to D converter have this to provide the clock signal to the correct the clock input. We have to also change that one here and there. Wow. Yeah. All right. So that is exactly the reason why I'm not requiring the low pass filter to put on the exercise. Yes, you have a question. What number? DB00 is which oh yeah, that one. Yes, DB00. Yeah, maybe. Okay. Let's take a closer look at everything now. One by one. Okay, where did it go? So let's take the last piece what we put there. Easy A to D converter, easy ADC. For routing the signal, we had to put that one here. So the input is actually coming from port 0 pin 3. Okay, that was the way to route the signal to this block. And okay, then this actually takes the clock signal is coming from the analog clock 0 select. We used to have that 8-bit counter connected to that one, but we cannot use it since that's the only way to get the correct clock rate to our easy ADC. Okay, so that reason I had to take analog column clock not from 0, but analog clock 1 select. So I change it to this one. And this is now connected to DBB00. Wow. I know. Confusing. At least for me, this is very confusing. Not the perfect system, but it's the best we have. And we have a data acquisition system there. We have gain, analog filter, ADC. Wow. Okay, let me generate the configuration files and show you some stuff. Okay, I was a little bit fast here. So basically, let's take a look at the A to D converter here. How does it go? Yeah, okay, there. There we have the sample rate and resolution. So currently sampling rate is very slow. I think this is on kilo samples per second, or is it? Let me take a look at the easy A to D converter. The data sheet. I told you something about we need about 100 hertz, 100 samples per second. So basically, we can get about 100 samples per second if we have either 10, 11, or 12-bit resolution. Those are the only resolutions where you can actually have the sample rate at about 100 hertz. So it's up to you which one to choose. Just for fun, I will then select, say, 12-bit and sample rate, well, 0.12 kilo samples per second. Yeah. There. That's okay. Maybe. Definitely maybe. All right. So unsigned integers, resolution 12 bits and about 120 samples per second. Then some hints how to do the this running average. Okay, one more thing. You probably also want to put the LCD somewhere on the design, you know. Might be a good idea. For debugging, there's no other ways to debug these PSoC ones in our system. The full emulators are available, but it's not part of it. Okay, so basically main file is empty and EC8DC int.asm actually have the interrupt service routine. Yes, you have a question. Huh? Counter 8, that one. That is connected now to the analog clock select 1. DBB00. And that actually is now connected here. Yeah. So analog clock 1 select is used as the analog column clock for the filter. Good. Now the interrupt service routine. So in here, we have a section where we can put your own code. There we go. There's a section that says sample data is now in iResult. And there's insert your custom code below this banner and insert your custom code above this banner. So in here, we actually can have long call to your own routine. Calc mean or something like that. Your own C routine that does the calculations. That's the easy ADC int.asm. So A to D converter interrupt service routine. But actually you might want to also add here the preserve registers and restore registers. So wait a minute. Should you need to use the register A, you must press the value and restore. Okay. Push X. Pop X. Right. Because it says here. Okay. If you need to use the X register, we don't know that what the compiler does for the C code. It probably uses also the X register there for calculations. I'm pretty sure of that. Then basically we just need to push and pop, and in between you have the call to your routine. So some assembly is always required. This is embedded code. And of course, now we need to also have the in here we have the oops. The routine which is called on every single time the A to D conversion is ready. There. Okay. Right. And there you would have basically the couple of variables. Long int stemp starts from 0 and integer, just for fun, integer or for ntemp starts from 0. Ntemp plus plus and then stemp plus equals to ADC result. That's your way, your job to find out how to get the A to D conversion result. Actually, it's quite easy. It's basically here. That one. That calculates the running sum and also keep account on how many the values there are on this sum. And why I used long int instead of just int. Int is 16 bits. And we have 12 bits of data. And we might actually have about 50 values on that running sum. 50 is more than 4 bits. So it means that you need to have a long integer to save the value there. Yes, you could. Yeah, you also can do that kind of thing. So yeah, but then you will lose the resolution and yeah. But anyways, this is still a safe way of doing the calculations. Then when you divide it by the number, then you just need the integer. Okay. Okay. So, any questions? So you probably have nothing but questions. All right. I just wish this was easier, but on the other hand, if it was easy, then someone else would do it. Right. So you wouldn't need engineers to do the coding for this if it was easy. Okay, so just a quick review. We were about to do this kind of thingy. A sensor goes to first an amplifier, then low pass filter, then A to D converter, and then basically you do software downsampling, and finally putting the value on the LCD. The hard part was to get all of this correct, since you had to have in order for that one to work, you needed to have this switch capacitor filter clock. On the other hand, this sample clock for the A to D converter overwrote some of that. And it seems very simple to just, connect wires like that, but in reality, you need to fiddle between, this wire here was eventually, okay. The first wire is actually right here. No, not there. Okay, sorry. Right here. Input signal to gain. It takes all of that multiplexer, that the even pin multiplexer to select, analog select, and then to input. That was the first wire. Second wire, that was easy. Right there. Okay. First wire actually is here. First wire is not that one, that's the second wire. First wire is here. Plus that one. Then we have the second wire right here. Oops. It doesn't highlight it, of course. Then third wire actually is on pin. And yeah. Well, this is one block, the sample hoard, and that one is one block, A2D converter. And finally, we get the data out with the software. And there we basically have the calculation of the running average. You need to calculate the running sum and how many values there are on the sum. It's done here, which is basically a function call inside of the easyadc int.afm. Okay. And of course, some main code should go there. Starting all the blocks what you have there, including PGA, this block has to be started, otherwise it doesn't work. Low pass filter block must be started, and that's not enough. You have to start also the counter to provide the signal. Then you have to start the ADC block, ACDC block, and the LCD. So 5 different blocks must be started, at least. Okay, and then good luck for the exercise. You will need it.